Well, let's continue. Another example of a time discretization of the heat equation would be the simple implicit method, or the backward time-centered space method. We had an example on that. It was in exercise 4, I think. And there you should also be able, and we have done training on that, how the boundary conditions are implemented, how you to set up the linear system. We get a tridiagonal linear system. And in the end, we get a method that is of the same order as the explicit Euler method, that is first order in time, second order in space. But it is convergent for all von Neumann numbers are larger equal 0. So that means it is unconditionally stable. Next in the row of the model equations was the linear advection equation. And that we did not look up in detail, that was the wave equation. My colleague Rader Christofferson had covered that though in the demo lectures. But the focus has been on the linear advection equation. So ut plus c ux equal to 0. That is the linear advection equation. C is the constant advection speed. Now I have to ask you again about the number, because I changed my numbering.
10.
Thank you. So, and again here, the same applies as we already discussed in the beginning regarding the Burgers equation, regarding the boundary conditions. Here it is much easier than for the Burgers equation, because here the characteristic, the slope of the characteristics is given by this constant advection speed c. And then we have to decide whether c is positive. Then we have inflow at the left, outflow at the right, or the opposite, and accordingly give the boundary conditions. Also here we have the FTCS scheme, and it has the same stencil, the center point at the old time level, that is at xj, and the neighbor at xj plus 1, to determine the value at the new time level. It turns out that this method is consistent but unstable. And that means by Lux equivalence theorem it is not convergent. So that is by Lux equivalence theorem. That means it is not convergent. So that means that is useless. We cannot work with that. However, if we would use then in time another method, not the explicit Euler method, but we would use the Range-Kutta method of higher order, say third order, fourth order. Heun doesn't do it either. Then we can get it stable. That was an example that we looked at in the extra exercises before Easter. However, we have a method that we investigated here in much detail. That was the explicit upwind method. And if we assume that the advection speed is larger than 0, advection from left to right, then our stencil is such that we take the value, how to determine the space derivative, from where the wind is blowing, the upwind side, that is here to the left. So then that to determine the value at the new time level. And if we think of this here as time and space, what it is, this is x, this is t, then we can easily introduce here the characteristic. And if we do that, say we have here the characteristic, and then we know that the slope of the characteristic is equal to the advection speed. And that means, and this distance here, that is delta t, the distance here, that is delta x, but the distance here, that is then the distance that the flow has traveled in the time step size, in the time instant time difference delta t. So that means this is c times delta t. And that gives us already the idea of the CFL condition, Courant-Friedrichs-Levy condition, that this distance here has to be smaller than the grid spacing, because if we go outside, then we cannot do an interpolation. We do an extrapolation, and that is always dangerous. And as you might have seen, if you do that, you use the explicit upwind method with a current number larger than 1, it's unstable. So from that, we get then the stability condition, we get the CFL condition, and that is that the current number, which we denote by capital C, is the distance traveled by the flow or whatever problem we consider in the time difference delta t, divided by delta x, that has to be smaller or equal than 1. And if we do it really carefully here, it is okay, but if we do it for the general case, we would have to take the absolute values. Of course, when we have c negative, then we will take the value to the right. We will not take this uj minus 1, we will take uj plus 1, because then flow is going that way. And that is also what we investigated in one of the exercises. So that is the stability condition here, and that we can show by the von Neumann analysis, von Neumann stability analysis. Regarding accuracy, we can also show that the truncation error is of order delta t in time and delta x in space. So it's only first order in time and space. However, when we apply this for the current number 1 or minus 1, then we get it exact. So that means the upwind method, explicit upwind method, is exact for, in our case, just the C, the capital C, the current number 1. Why is that? Because then the characteristic simply comes from this point here, and if we write down what the numerical method gives us, it gives us exactly the same as the analytical solution would give us. The value here is determined by the value here, because on the characteristics the solution is constant. We have also looked at the implicit upwind method. We get a bidiagonal linear system that we can easily solve. The method has the same truncation error, but it is unconditionally stable. So we can use any value of delta t. And by Lax equivalence theorem, that it is convergent for all delta t larger 0. So that is a very simple equation, but it is not so easy to solve. And why don't we use always c equal to 1, current number 1? Because we have nonlinear problems usually, and there we had the example from Berger's equation. So it is not possible to do that. So that is the Berger's equation, and we had it, let's see, I think we are now at number 11. The general formulation is of a conservation law, because we had also an example that was the traffic flow equation, conservation law, and the general equation there is ut plus, we have a flux function f of u, we take the x derivative, and we take on the right hand side, we have a viscosity coefficient times the second derivative. And for the Burgers equation, then this flux function f of u is very simple. It is u squared half. And then we can get the characteristics from that. By the curves in time space dx of t dt, which is given by f prime of u. So in that case, for the Burgers equation, that would be u itself. That is what we discussed in the beginning. Then we can investigate so-called Riemann problems when we have constant conditions, piecewise constant conditions with just a jump. We have seen we can get a shock if UL is larger than UR. We can get a rarefaction wave when UL is smaller than UR for the Burgers equation. You saw it is just the opposite for the traffic flow equation. And we can solve these conservation laws like the inviscid Burgers equation when we neglect this, when we say nu is 0, then we have the inviscid Burgers equation. So we can solve these equations by a conservative finite difference method. So, or FDM in conservation form. And that is when we do the discretization, then we do that at the grid point J. Now we have the subscript is the space, the superscript the time level, minus un divided by delta t, plus, and then we introduce numerical flux functions. We call that fj plus 1/2 at the old time level minus fj minus 1/2 at the old time level divided by delta x is equal to 0. That is for nu equal to 0. So then we are talking about the inviscid Burgers equation. We can also use that for the viscous Burgers equation, or for the Burgers equation. Then we would just take the same discretization as for the heat equation for this. But the difficult part is the nonlinear part. And where the fj plus 1/2 is then a numerical flux function. And we just need one of them because then we can just shift index to get the other. We need a consistency condition. So, and in our case, we have usually fj plus 1/2. That is a function. Fj plus 1/2 is a function of the next neighbors, uj and uj plus 1. So when we would have uj minus 1/2, that would be a function of uj minus 1 and uj. And we looked in particular to one example for that, that is the explicit upwind method. So the explicit upwind method. There we had two formulations. One was that we have to determine in any way. We have to determine the characteristic speed. We do that by using essentially the Rankine-Guignot condition. And then we have the characteristic speed, and then it determines then, as the C does for the linear advection equation, whether we have flow from left to right, when this aj plus 1/2 characteristic speed for the explicit upwind method is positive, or the opposite. So, but one way to write it very briefly is the following, that we say the fj plus 1/2. We don't write the time, because that is then in our case always at the old time level. That is then the form that we can use in without if statement. So here we use then the flux function that we have from the conservation law. In our case it would be f of uj would be uj squared half plus f of uj plus 1, which would be uj plus 1 squared half, and minus, and now we have here this characteristic speed that has to be determined in this special way, and that you should know. And then we have to multiply that by the difference in our flow variable, which is then uj plus 1 minus uj. So that is the numerical flux function of the explicit of the upwind method. We could also use it for the implicit one, but that we did not discuss. And we found out that the characteristic speed that is for the inviscid Burgers equation, and that is something that you should know how to derive that, is aj plus 1/2. It turns out it's simply the average, the arithmetic average of the flow variable. So that is something, how it is derived, that you should know. And then for that you will need the Rankine-Guignot condition when uj and uj plus 1 are different. And it will be the characteristic speed, that is the f prime of u, with the value uj or uj plus 1 if they are equal. We have a stability condition see now, I lost track again on my numbering. That, did we give it the number here? 13, thank you. So then that is 14 here. Thanks you. And then that is then 15. And it turns out that we have to look at the maximum of the Courant numbers that are involved, and they are determined then by the characteristic speeds, and that means here we look then at the maximum of j. The characteristic speeds are the f prime of uj. For the inviscid Burgers equation, this is just uj, so the absolute value of uj times the time step size delta t divided by the grid spacing. And the condition is, for the explicit upwind method, that this has to be smaller or equal than 1. The accuracy of the method is like the explicit upwind method for the inviscid, for the linear advection equation, first order in time, first order in space. Well, we had also alternatives there. That is the Lax-Friedrichs method. So the distinction is now just by the flux function, by the numerical flux function. Lax-Friedrichs method. It starts very similar as the upwind method. That is the numerical flux function for Lax-Friedrichs is also here starting with the arithmetic average of the flux functions evaluated at uj and uj plus 1. But instead of choosing this particular way of characteristic speed determined by Rankine-Grignot condition and characteristic speed, we simply choose here the ratio of delta x and delta t times uj plus 1 minus uj. So that is much simpler, but you remember this gets very dissipative when delta t gets large, because this is related to the numerical viscosity. Actually, the numerical viscosity would be delta x squared divided by delta t, and we have also the 2 in front. You see that when you divide by delta x, multiply by delta x, then you see this coefficient here is what you would also get when you would do the discretization of the Burgers equation. Then it would be physical nu. It would not be here, you have the half, but here it's just numerical. So therefore, we can say that this method is very dissipative. That means it behaves as if you would have a large viscosity, dissipative, for delta t or current number to 0. So it becomes essentially useless. But it's still a method that if you lose all hope in solving a problem, you can still try to use, but then you should use it near current number 1. There it's not that bad. Instead, it's better to use the local X-Radix method. That is something that doesn't suffer from this problem. The other name for that is Rusanov method. Local X-Radix or Rusanov method. And that is very similar, but it has a slight difference. Fj plus 1/2 is equal to, it starts the same, they are all the same, these methods. In the beginning, average of the flux functions, but then it has another characteristic speed other than the upwind method times the difference in the flow variable. And this time the Aj plus 1/2 is the following. Where for the local X-Radix or the Rusanov method, this particular characteristic speed entering the numerical flux function is the maximum of the modulus of the characteristic speed evaluated with uj and the modulus of the characteristic speed evaluated with uj plus 1. And that means that we have the characteristic speed entering the local X-Radix or Rusanov method for the inviscid Burgers equation is then the modulus of, this is just then the uj, modulus of uj, and this is just the modulus of uj plus 1. So that is the difference. That is for inviscid Burgers equation. And that does not suffer from this drawback of the X-Radix method. That is, by the way, also a useful method for systems. Then these f primes, they will be Jacobian matrices, and then you choose the largest eigenvalue. That is the spectral radius of those with uj and uj plus 1. That is something that we do in the follow-up course. Okay, that were our main time-dependent problems. Then we looked into the numerical solution of linear systems, but we had that before, but we can also revert it, that we first look at the elliptic problems motivating the linear systems. And that was then what was our chapter 10. So the 9, we had the 9 first, but I take now the 10 first. The Poisson equation. And that is, now I have to remember my numbering again. Where are we? You know it better than me. You have the notes. 18. Thank you. Uxx plus uyy is equal to some given right-hand side. So now we have x and y. We have our stencil, the center point ij, the western neighbor I minus 1, eastern neighbor I plus 1, northern neighbor j plus 1, southern neighbor j minus 1, and they are involved when we do the discretization. So this now is x, and this is y. That leads to a block tridiagonal linear system, or a block pentadiagonal linear system, that we discussed in exercise 11. And the thing that is important here is diagonal dominance. So that is that means that the coefficient that is in the diagonal has to be larger or equal the sum of that row that we consider, except for the value that we have in the diagonal of the modulus of aij. That has to be true for all I from 1 to n, if we have an n by n system. And then the other condition that we need is that we have not here a larger equal, but we have at least for one I a larger than. So we have here the sum of j from 1 to n. J is not equal to I of the modulus of aij. And that is for at least one row I. If we have these two conditions fulfilled, then the matrix is called diagonally dominant. And that is useful because then we can do iterative solution by the Jacobi method or the Gauss-Seidel method, and then we know that they will converge for any initial guess. So then I take therefore now reverse order. Now it comes, we had it differently. But now in this way I take then the number 9 after the number 10. Solution of linear systems. Of equations. So there we have learned about direct methods. And we have learned in 1D, when we have a 1D problem. For example, if we would solve the heat equation by an implicit method, I already mentioned we get a tridiagonal linear system, and that we can then solve by the Thomas algorithm, or same name but usually used in CFD, the tridiagonal matrix algorithm. So that takes about, that is, say, if we have 8 times nj, that is the number of unknowns. So we are in 1D here, so we have nj unknowns. Then it takes about 8 times nj floating point operations. Floating point operations. So that is useful when you want to estimate the work for a method. Then it gives you then. That is based on doing LU decomposition without pivoting. Again, here we need diagonal dominance for that, using forward-backward substitution. And then this is only goes with the number of unknowns, which is much better than if you would do here full LU decomposition for a full matrix. Then that would be nj to the power 3, which is a big difference. The second type of methods that we discussed were iterative methods. And there we discussed in particular the Jacobi method. There we solve for the unknown uij by taking the rest at the old iteration level. So it comes down to a few operations. But then we always need 2 levels, the old iteration level, the new iteration level. When we just override directly by the new value that we have the Gauss-Seidel method. So that is converges about twice as fast as the Jacobi method. And this is, of course, then easier to code because we need just one level where we override directly. And the method that we also used, in particular also in the last exercise for solving the elliptic equation, the Poisson equation for the pressure correction, when we solve the Navier-Stokes equation, is the successive over-relaxation. Successive over-relaxation. So that is essentially Gauss-Seidel, but then you correct more than you would do with Gauss-Seidel. And then this relaxation parameter, omega, is really important. And for some examples that we have, for example, Dirichlet boundary conditions, then we know what this parameter is, and then you saw demonstrations by my colleague Reda Christoffersen that this makes a big difference using then SOR to this. This takes then order, if we have nj unknowns, it would be just one dimension. It would be order of nj squared iterations, while this would only take order of nj iterations. So it makes a big difference. Other methods that are available that were just mentioned, like multigrid, Krylov methods, but this is something that is numerical linear algebra, that is outside the scope of this course. By the way, you should also be able to do a little coding of that in MATLAB. You can expect also some MATLAB problems in the exam. It will not be a focus, but there will be MATLAB questions. And that was, I think, one in an old exam. And you should also be able to implement a stopping criterion. So that is also needed here, that we need to say when have we solved the linear system accurately enough to stop further iterations. And in any case, when we stop, we will have some iteration error. But the iteration error, if that is smaller than the truncation error, then we are fine. We don't need to go any further. We had also examples on that, where we looked at the difference between the truncation error, between the discretization error, that is the error between our numerical solution and the exact solution of the PDE. And the iteration error is the error that we have when we solve our linear system iteratively with respect to solving it exactly, for example, by a direct method. That's the difference. When we solve a linear system, we have already done the discretization. So we will always have this discretization error. So that is something that we discussed in exercise 10. By the way, all exercises are relevant regarding numerics and to some part also the MATLAB parts. '11 was devoted to the 2D convection diffusion equation. So the equation, let's see, I keep loss of my numbering. Is it 19? Right. 20, thank you. We have a time derivative of our scalar u. We have a transport in x direction and in y direction. C1, C2, they are components of the constant advection velocity. And on the right-hand side, we have again our diffusion coefficient or thermal diffusivity, if we have a heat transfer problem, and now second derivatives in x and y, where the c is a vector with the components c1 and c2 is the advection velocity. And the alpha greater 0 is the diffusion coefficient. For this particular example, we saw that the forward time-centered space method works. It works thanks to the viscous term. So that gives us some additional stability, and under a stability condition, this can be solved then in a stable way. So that means the FTCS is stable. We derived that. That is a little bit more involved. I write it down here for completeness. We have two conditions, 1 over 2 alpha, 1 over delta x squared plus 1 over delta y squared. So that corresponds to the condition that we get from would get from just solving a problem for just a 2D diffusion equation. But when we have convection diffusion, we get some combination. Here we get 2 alpha c1 squared plus c2 squared. And we get that the truncation error of this method is of order, of course, only first order in time, but it's second order in space. So that is a good thing. And that was actually used then for solving our Navier-Stokes equations, the momentum equations, the Navier-Stokes equations. We can also use other methods here. We could use an upwind method for this, or could use also Lex-Friedrichs, which I would not recommend at all. local Lux-Radix or Rusanov. This is usually solved by a centered scheme. That is a good method for the second derivatives. In time, we could also get more accurate using a Runge-Kutta method. Hoyne would give us second order. Classical Runge-Kutta method would give us fourth order. And then the last chapter, 12, was on the introduction to the discretization of the 2D incompressible Navier-Stokes equations. The method that we looked at here, there are many, but the one that we looked at is quite a popular one. That is the projection method. I already say here, this is not pensum for the exam, but it is useful to know. How do we do it? The x and y momentum equations are solved on a staggered grid. That is something very nice. And by what I just said, by the FTCS that we have just discussed. The staggered grid, remember, we have a cell where we have the pressure Pij. Here we have the Uij, and here we have the Vij. So that gives the numbering. So that means the scalar values, pressure, if we would have temperature, if we would have a concentration or a turbulence model, whatever, all these values are in the cell center. And at the faces with the normal in the x direction, we have the U. At faces with the normal in the y direction, we have V. If we would have a third dimension, it would correspondingly be on the faces with the normal in the z direction. From this, we get preliminary velocity components U star, or intermediate velocity components. And then we solve a Poisson equation for the pressure correction. So you see here we need our knowledge that we acquired for solving 2D convection diffusion equations. And now we need our knowledge to solve elliptic equations. Poisson equation for pressure correction. That is the P prime. That is the pressure that we really are interested in at the new time level and the value that we have at the old time level. That is solved by standard finite difference method that we discussed for the Poisson equation. And the solution of the linear system that is done by the in the Sula algorithm, linear system, actually it is updated iteratively because that is the linear system solved by SOR in that example. When we are done with that, then we get the pressure at the new time level by the one at the old time level plus the p prime. So we solve for the p prime. So the right-hand side is essentially the, I think, minus the divergence of the preliminary velocity. And when we have the p prime, we can also then correct our velocity components, because they do not, that is the intermediate or preliminary ones, do not yet fulfill the divergence-free condition. That is that they don't fulfill the continuity equations, the continuity equation, so that they will be corrected. And that is done essentially by using the preliminary values minus, and then we have here a delta t divided by the density, and then we get here a discretization of the dp dx. And because it is just the neighbors, it's so nice here. You see here, we'll have here just the pressure correction also at pi plus 1, and pi would be involved here. And also for vn plus 1, that is the preliminary value that we have determined just by the FTCS without considering the continuity equation, just the momentum equation. And then we do here a correction taking the derivatives with respect to y. That is then here the pi j plus 1 minus the pi j divided by delta y. That is then the approximation. And then we go on. Okay, so that is the outline of how we can solve the 2D incompressible Navier-Stokes equations. For tomorrow, as I said in the beginning, we'll look at the exam of last year. So I really recommend you to look at that and try to solve it. And we will go to a couple of problems, and as many as we can do in the last lecture tomorrow. Okay.